Look here at example 4. We've got the graph of the height of a paper airplane off the ground, S of t, measured in feet, t seconds after it's launched into the air. So this is the time axis here. This is measured in seconds. And the y-axis here, this is measured in feet. And that's the height off of the ground. So it says approximate the average velocity for the first 7 seconds of flight, t between 0 and 7. So we're looking at, once again, t values between 0 and 7. So here's 5, 6, 7. And so to get that average velocity, that's going to be your, the average velocity. That's going to be the change in height over the change in time. So let's see, the change in height. So we're starting at 0, 0. We come up, looks like, if I estimate this, see how high this is off the ground, 1, 2, 3. So it looks like we've gone 3 feet up in 7 seconds. So it looks like it's 3/7 feet per second. It's positive because we're rising, we're going into the air, and so that would be our average velocity. Is this a good approximation for v of t over this time interval? Well, remember what we're doing is we're approximating the slopes throughout the entire interval by this slope, the slope between these 2 points. So is it a good approximation? Well, it looks like it starts off from rest initially, and then the slopes are slowly increasing. So I guess that's sort of the question is sort of looking at, you know, the goodness of fit is in the eye of the beholder. I mean, it seems to do a reasonable job, but we know that the actual instantaneous velocity starts at 0 and constantly rises. Next question, what is the highest altitude the paper airplane has reached? When did this happen? So once again, looking at this graph, the points on this graph are t comma s of t. And so if I'm looking for the highest altitude, I'm looking for the largest value of s of t, which would be right here, according to this graph. So the highest altitude would be 11.25 feet. When did this happen? When the t was 15. So that's 15 seconds after the paper airplane has left the ground. How long was the paper airplane in flight? Well, once again, the coordinates here are time comma s of t, or time comma height. So the thing starts from the ground, rises up to 11.25 feet off the ground, and then comes right back down to the ground. How long does that take? 20 seconds. When is v of t positive? When is v of t negative? When is v of t 0? What about the absolute value of v of t? So remember, v of t is the velocity. So the velocity, remember, that's the derivative of the position. Geometrically, we're looking at the slope. So we start off here. This really looks like the velocity is 0 here. So it looks like the velocity at 0 is 0. And then the slopes are positive until we get to this point where the velocity is 0 again at the highest value. So v of t is greater than 0. In other words, it's positive for t values between 0 and 15. Now once you get past 15, the slopes are negative all the way down to and including 20. So v of t is less than 0 or negative between t is 15 up to and including t is 20. So it's going to strike the ground with some kind of velocity here. So once again, increasing, positive slopes, we're heading up to the maximum, and then we're heading down. Where is v of t equal to 0? What appears to be 0 initially here, and again when t is 15. So when it starts off from rest is what v of 0 is 0. This is the same as the from rest condition. And then it also zeroes out when it gets to the maximum height. Then it asks for the absolute value of v of t. Remember, that's the speed. Okay? So the speed is always going to either be positive or 0 because it's an absolute value. So the speed is positive. Well, it's positive because it's positive and heading upwards from 0 to 15. It's positive but heading downwards from 15 up to 20. Okay. Is a of t ever positive? Explain. So a of t, we got to remember what that is. A of t is the second derivative of the position. So it's the first derivative of the velocity. Now the velocity, remember, is the slope on the curve. So the acceleration is the derivative of the slope, which means we're looking at the rate of change of the slope. So let's take a look here what's going on with these slopes. So if I kind of just rough in these slopes, notice here the slopes start at 0 and then they start to increase. Things are getting steeper, right? So a prime of t, excuse me, a of t being positive, so a of t bigger than 0 being positive means that the slopes are increasing. So the slopes are increasing throughout here. Okay, slope, because the curve, these slopes are positive and they're getting steeper until like right around here. Then the slopes decrease, they zero out, and then they go negative. Okay, so a of t would be positive here in this region. All right, and if we wanted to ballpark it, I would say between 0 and 10. So a of t, second derivative of position, first derivative of velocity. It's the rate of change of the slopes. Are the slopes increasing? In this case, we have positive slopes getting steeper. So yeah, the acceleration is, over that interval, increasing. Beyond 10, the slopes are always decreasing. The slopes are getting less steep and positive, then they zero out. Then they're getting more steep and negative. So that means that the slopes are decreasing then for the rest of the journey. So that'll do it for example 4.